speaker of this afternoon session is Professor Egor Shelukhin from the University of Montreal. He is recipient of the Frontier of Science Award. He will talk about the Hofer-Zehnder conjecture. Let's welcome him.
Thank you very much. I would like to start by thanking the organizers for this tremendous event and for the possibility for me to participate in it. I would also like to thank the audience for being here. I know it's late in the week and late in the day. So I will talk about the Hofer-Zehnder conjecture. And my first goal is to formulate the Hofer-Zehnder conjecture. To formulate the Hofer-Zehnder conjecture and to motivate it, I'd like to talk about Arnold's conjecture, starting with the Poincare-Birkhoff theorem. All right. And by the way, I'd like to add, so please ask questions. So we have plenty of time. So the Poincare-Birkhoff theorem, conjectured by Poincare in 1912 and proved by Birkhoff in 1913 mostly and 1925 completely, is the following. So consider an annulus, so S1 times 0, 1, and an area-preserving homeomorphism of the annulus isotopic to the identity by an isotopy which rotates the boundary components of the annulus in opposite directions, so strictly opposite directions. In this case, the area-preserving homeomorphism has at least two fixed points. And so the two fixed points under a twist condition. Right, so fixed points are points x that are fixed by the homeomorphism. Okay. And by the way, Birkhoff's proof worked in 1913 for one fixed point, in 1925 for two fixed points. So that's why there are two proofs. So this theorem has been improved and reproved many, many times along the years. It inspired numerous developments in two-dimensional conservative dynamics. And perhaps the optimal version of this theorem was proved by John Franks. And one manifestation of his proof is the following result. So consider an area and orientation preserving homeomorphism of the standard two-sphere. And assume that it has at least three fixed points. Then its number of periodic points is infinite. So it has infinitely many periodic points, where here periodic points, so the set of periodic points is just the union of the fixed points of all the iterations of phi. So phi squared, etc., etc. All right. So a few remarks about this theorem. So first of all, every such homeomorphism has at least two fixed points. So 3 is one more than absolutely necessary. Proof of at least 2 goes by deleting 1 and using the Brouwer plane translation theorem in the complement, which is a disk, and then using area preservation to get the contradiction if there's no second fixed point. So, then one might wonder, well, you know, Euler characteristic of the sphere is 2, so maybe there are two fixed points always. But actually, without area preservation, that's not the case. Of course, at least one you can always get, right? By just applying the, intersection index argument and taking the limit. But in fact, there is a homeomorphism of, even a diffeomorphism of S2 with just one fixed point. Of course, it does not preserve area. And you can envision it as follows. You take the plane C and you just shift Z to Z plus 1. And then compactify to the sphere, right? And then the infinity will be the unique fixed point. And so the dynamics is gonna look something like this. So this is infinity, and then there are all this kind of circles along which you always shift, right? Parabolic dynamics. All right, and finally, the theorem itself of Frank's is also sharp. So there is a diffeomorphism of S2 with exactly two fixed points, which are also exactly the set of all the periodic points, right? So you can see it as follows in the same picture. So you just look at Z goes to rotation of Z by angle theta, and again compactify. In another language, you can take a sphere and you can rotate by an angle of theta, which is irrational in the sense that theta over 2 pi is irrational. Right? And then all the periodic points are going to be the north and the south pole, which are also the fixed points. Yes. Well, here multiplicities is just one. All the multiplicities are one. Yes. No. I said if there is at least 3 fixed points, then there's infinitely many periodic points. And then the argument here shows that there is at least 2. Yes. But we will get to the multiplicity in a moment. It is going to be important in maybe 1 or 2 slides, so to say. All right, so we rotate the sphere, and the dynamics looks now like this. There's this periodic point, this periodic point. Everything else never comes back to itself because the angle is irrational. So this is an example. Further, such examples can be obtained by Anosov-Katok conjugation method. They're called pseudo-rotations. Of course, this is a genuine rotation, but there are other transformations with a similar property, but they're not exactly the same. All right. So Poincare-Birkhoff theorem not only inspired numerous developments in 2D conservative dynamics, but it also inspired Arnold. So what Arnold noticed is that, okay, let's assume that phi, our homeomorphism, is smooth, it's a diffeomorphism, and let's assume for simplicity that it actually does shift the boundary component. So restriction to every boundary component is not the identity. It really does shift. So in this case, Poincare-Birkhoff would follow from the following statement, that the Hamiltonian diffeomorphism of the two torus must have at least 3 fixed points in the torus. Okay. So here Hamiltonian means the following. So it is area preserving, it is isotopic to the identity, and also there is no area flux through curves. Okay, so you cannot kind of, if you take a curve and you look what happens to this curve under the isotopy, the area that is swiped out must be 0. Okay. So in this case, that's the meaning of Hamiltonian. And the argument looks something like this, what I drew here. So you take your annulus diffeomorphism, you take a reflected copy of the same annulus diffeomorphism, then you use the boundary conditions to glue 2 handles on which there are no fixed points. Right? And then if you know that this gadget has at least 3 fixed points, at least 2 of them are going to be on one side. Either this one or that one, but we don't mind. Okay. So this is the argument. And finally, maybe a remark that this is actually sharp, because there is a smooth function on T2 with exactly 3 critical points. Right? So if I'm not mistaken, you can write it as, so if you have P and Q coordinates, so it's a sine P sine Q times sine P plus Q. So, and these critical points, there's a non-degenerate maximum, non-degenerate minimum, and a degenerate critical point, which is a monkey saddle. So it's kind of, you have two saddles which have collided. Okay, 2 saddles. All right, and then what we can do is we can solve Hamilton's equation, P dot equal minus df dq, Q dot equal df dp. All right, and we can solve it for time epsilon, which is very small. Okay. Then it is easy to see that we get a Hamiltonian diffeomorphism, and also its fixed points are exactly these critical points of the function. So there are 3 of them. So that's why this theorem is sharp. Finally, actually, so if we require this psi to be non-degenerate, so if we require its graph to be transverse to the diagonal, then the lower bound here would be 4. Okay. And this again has to do with the possibility here of some critical points or some fixed points colliding. All right. So after considering this argument, Arnold conjectured many other lower bounds of this kind. And by now, quite a lot is known. And I would just like to present one thing that is known. So first of all, what is the setting? So the setting is the following: that M omega be a closed symplectic manifold, so dimension 2n, and omega is a closed 2 form that is non-degenerate. So it defines as isomorphism between tangent and cotangent bond. Then we look at the group of Hamiltonian diffeomorphisms. So a Hamiltonian diffeomorphism is a diffeomorphism of the manifold, isotopic to the identity, and the vector field, the time-dependent vector field, which generates it, is given by this omega isomorphism from a time-dependent function. Right? So from a smooth function, depending on time and coordinate in the space, that is one periodic in time. Okay. All right, and then we know by work of many people over many years that in this setting, assuming, let's say, that the diffeomorphism is non-degenerate, so the graph of the diffeomorphism is transverse to the diagonal in m times m, that the number of fixed points is always at least the dimension of the homology with coefficients in some field. So, right? And maybe one remark is that one consider only the fixed points such that the loop formed by these fixed points by the isotopy is contractible. This actually does not depend on the isotopy you choose to generate your Hamiltonian diffeomorphism. So the consequence of basically existence of Floer theory. Okay. All right, and this works for all fields K. Okay. So then, as I said, if M is the 2 torus, the answer, the lower bound would be 4, right? In the non-degenerate situation, right? Because that's the dimension of homology of the torus. Okay, so maybe a few remarks. So first of all, if phi has finitely many fixed points, but they are allowed to be degenerate, So this is exactly your comment about multiplicity, right? Then to get the lower bound, the dimension of homology, you should count these fixed points with weights. So the weight of every fixed point is a certain dimension of local homology. Okay, so for instance, in the example that we had before, with the 3 fixed points, the counts would be 1, 2, 1, where 2 is the weight of this degenerate fixed point, the monkey saddle, right? So 2 saddles have collided. Okay. All right, and maybe another remark is that in positive characteristic, this was known until very recently only for monotone manifolds, monotone symplectic manifolds, namely manifolds where the first-gen class and omega 1 are proportional on pi 2. So I wrote here k greater or equal to 0. Usually monotone is strictly greater, but I wanted to include symplectically aspherical case, so where omega a is always 0 for all a in pi 2. Okay. So this is the classical setting, the proof of Floer from long time ago. Okay. And a slightly more recent argument proved the same for so-called semi-positive closed symplectic manifolds, but also more recent, but also rather classical argument of Hofer and Salomon. So semi-positive is a slightly less restrictive condition on first-gen class and omega on pi 2, which is, for instance, satisfied on for Calabi-Yau manifolds. So manifolds where first-gen class pairs with every pi 2 class trivially. When C1 is trivial on pi 2. So it's symplectically Calabi-Yau manifolds. And very recently, Abu Zaid and Blumberg have proven this for all closed symplectic manifolds. And I think Mohammed mentioned this this morning. Okay, so maybe one more comment. So I'm focusing on fields here, and there was also interesting recent development when one takes K to be a ring, for instance, Z. So it's work of Bai and Shu, and also Reschu. All right. So this is Arnold's conjecture. So the takeaway for now is that there's Frank's theorem, and then there's Arnold's conjecture. So based on these two results, Hofer and Zehnder have conjectured in their 1992 book, Hamiltonian Dynamics and Symplectic Invariance, the following. So this is actually just a copy-paste, a print screen from page 263 of their book. And okay, we can just read this out. So they said that based on recent proofs of Arnold's conjecture and Frank's theorem, one is tempted to conjecture that every Hamiltonian map on a compact symplectic manifold M omega, possessing more fixed points than necessarily required by the V Arnold conjecture, possesses always infinitely many periodic points. So, of course, one can interpret this conjecture in several different ways. Here is one. So, homological interpretation. So, suppose that M omega is closed in phi Hamiltonian diffeomorphism, and suppose that the count of fixed points of this Hamiltonian diffeomorphism is bigger than the dimension of homology with coefficients in a field. Then there are infinitely many periodic points. Okay? And this count appeared earlier. So this is this homological count where you count fixed points with multiplicities. Of course, if there are finitely many, if there are infinitely many, you don't mind. There are just infinitely many. Right? Okay. Yes. Yes. In principle, it could affect. So, okay, actually, this is a great question. So, once you, okay, first of all, if phi is non-degenerate, it does not affect. Because if phi is non-degenerate, this count is just honestly the count of, you know, fixed points. Then if you fix a phi with finitely many, then for all large characteristics, you get the same number. So, and it's the same number as for Q. But in general, you can have some torsion in the local homology, and that's going to affect a little bit. All right. So then the result I'm talking about today is the following. So theorem, let's assume that M omega is monotone, and the quantum homology of the manifold satisfies certain condition. It is, so its even part is semi-simple. Then Hofer-Zehnder conjecture, interpreted homologically, is true. Okay. So instead of explaining in detail what is quantum cohomology and what does it mean that it is semi-simple, I would like to just give you an example. So consider a symplectic manifold which is just CPN. Okay. This result then implies that a non-degenerate Hamiltonian diffeomorphism of CPN with one more than necessary fixed points, so a number of fixed points n plus 2 or bigger, must have infinitely many periodic points. So the previous result for S2 is n equal 1, right? So if you have at least 3, you have infinitely many. So it's similar type of result. All right. And maybe one remark is that something else is known. So if characteristic of the field is 0, then in fact one gets a new p-periodic point for every sufficiently large prime. So then the number of periodic points of period k at least x grows at least like the primes. And you know, in the prime number theorem you have x over log x, but here it's x squared. The reason is if you have one new p-periodic point, you have a p-tuple. So you have slightly more. Okay, so perhaps before sketching the proof of this result, I would like to give some brief context, further context. So first of all, there is another conjecture called the Conley conjecture that for certain symplectic manifolds M omega satisfying certain conditions, every Hamiltonian diffeomorphism has infinitely many periodic points. Right? So for such manifolds, the conclusion of the Hofer-Zehnder conjecture holds without its assumption. Right? Okay, and there has been a lot of work on the Conley conjecture, and the state of the art is that it is true for closed symplectic manifolds with this property, that omega of a sphere times C1 of sphere is always non-positive for all spheres. So, you know, this is a quick way of saying either it's symplectically aspherical or Calabi-Yau or negatively monotone. So this coefficient in monotonicity is negative. Okay. So this is the result of a long development in the field, starting from work of Franks and Handel, Hingston for the standard 2n torus, Ginzburg in the symplectically aspherical case, and Ginzburg-Gurel, Hein, leading up to this state-of-the-art result of Ginzburg and Gurel.
Isn't it plausible based on what you know that if there is something finite immediately on constant quantum cohomology must have some field summons or something?
Great question. So, second of all, okay. so then indeed, for this to make sense, we want there to be at least one Hamiltonian diffeo with finitely many periodic points, and a conjecture, Chance-McDuff conjecture, states that in this case, the symplectic manifold must have many holomorphic spheres. So, for instance, it must be unirule. So, through every point, there must pass a non-constant holomorphic sphere. And of course, semi-simplicity of quantum cohomology implies this type of abundance of spheres, but it's kind of strong. So, in an ideal world, this would be the conjecture. And maybe another point is that there are other interpretations of what does it mean to have kind of extra fixed points. One of them is the following result of Ginzburg and Gurel from 2014. So they say if a Hamiltonian diffeomorphism of CPN has one fixed point which is hyperbolic, oh, I forgot to write hyperbolic. If it is hyperbolic, which it definitely does not have to be, then the diffeomorphism must have infinitely many periodic points. Similarly, if there's a fixed point such that the loop traced by the isotopy is of infinite order in first homology, then similarly the conclusion holds, and this is a result of Gurel, Ginzburg, Gurel, Orita, and I will make a comment. There's also a result of Sugimoto. I will say something about this a bit later. All right. So, very briefly, the idea of the proof of the result I'm talking about today is the following, that we should study Floer theoretic invariants of phi related to fixed points of phi, but ones that do not come from homological minimax in Floer theory. So the ones that do not correspond to spectral invariants, first of all. And secondly, we wish to study the behavior of these invariants under iterations. So what are these invariants? So these invariants are barcodes associated to Hamiltonian Floer homology. They have first appeared in a paper we wrote with Leonid Poltorovich in 2016, where we used them to study certain questions in Hofer's geometry. So the statement is essentially the following. You have a Hamiltonian diffeomorphism with finitely many fixed points. To this, there corresponds a finite multiset of intervals. So ij and mj, and intervals can be either finite, so ab, or infinite, a infinity, infinite only to the upper side. Right? And these barcodes, they can also be defined for functions. It comes from topological data analysis. They measure the appearance and disappearance of Floer cycles in sublevel homology of the Hamiltonian action function. And maybe just 2 points about the barcode. First of all, the number of infinite bars is the dimension of homology. And secondly, the total number of endpoints of bars, so number of infinite bars plus twice the number of finite bars, is actually this count of fixed points n phi k. Okay? And of course, this is bigger than twice the number of finite bars. So for the story today, we don't need the whole barcode. We only need the lengths of the bars, of the finite bars, and this can be extracted from Floer theory as follows. So set lambda 0 to be the universal Novikov ring with coefficients in our field. Right, so as Michael explained this morning, so these are power series, some ai t to the lambda I going to infinity. Sorry, I meant universal Novikov ring, excuse me. So all the lambda I are non-negative, coefficients are in k. Then we can set up Hamiltonian Floer theory with coefficients in this lambda 0. What happens is that we count solutions of Floer's equation, which I wrote here in green, going from x to y. We count them up to our translation. We look only look only at those that are rigid. Okay, but what's important is that every curve we count with a weight which is of the form t to power energy. Then one can show that this okay, first of all, that this is differential. Second of all, that this differential is defined over lambda 0. So all the coefficients have non-negative valuation, clearly, because energy is non-negative. And finally, that the homology is going to be isomorphic to certain number of copies of lambda 0. So the dimension of homology copies of lambda 0 plus sum of modules over lambda 0 of this kind, lambda 0 over t to the beta I lambda 0. Okay? And these beta I, if you, okay, let's say we arrange them in increasing order, are exactly the lengths of the finite bars. Okay, so we have the finite bars. So second ingredient is behavior under iteration. This uses the equivariant Pans product, and so originally it was called equivariant pair of Pans product by Paul Seidel in 2015 when he looked at iteration p equal to 2, the prime equal to 2, but in general it's I don't know, Pans for octopus with a prime number of legs. All right, so we worked this out with Jingyu Zhao in 2021. And perhaps maybe another general comment is that this is somehow an expression of Smith theory applied to the situation, to Hamiltonian Floer homology. And the most basic idea is that phi acts on fixed points of phi to the p. Just x goes to phi of x. Right, so, and then either a fixed point is fixed by phi, then it's a fixed point of phi, or not, in which case you have a p-tuple. Okay. So, long story short, this extends to Floer theory, and one can define an equivariant Floer theory with respect to this action. And if one, and as it goes with equivariant Floer theory is a module over the cohomology of the classifying space. Right, so, and if you take the Tate version, so if you localize with respect to the degree 2 variable t, then the equivariant Floer theory of phi to the p is closely related to the initial Floer theory of phi. So, okay, there is a little bit extension of coefficients, but what's really important here is this p stretch. So this means that the lambda 0 module structure, instead of just, so t acting by t now acts by t to power 1 over p. It means that all these bar lengths are stretched by a factor of p. Okay, and this isomorphism is achieved by counting certain multi-legged pants with a symmetry. So on the side of phi to the p, it's basically this symmetry, that phi acts on phi to the p, and on the side of many copies of phi, it just exchanges them. All right, right. So I forgot to say. So there's a intermediate step, which is an elementary algebraic isomorphism. So we have Floer homology of phi p stretched. We have Floer, okay, we have the cohomology of ZP with coefficients cohomology of phi to the p with this rotation action. And finally, we have this equivariant Pence map. And then one can show that both are isomorphisms. So first one is an elementary argument, which is slightly easier for p equal 2, slightly harder for p odd, but it is elementary. And on this side, the isomorphism between the Tate equivariant cohomologies is, first of all, there's a map. It's given by the equivariant pair of Pence. And secondly, it is invertible locally around every fixed point of phi. And for p equal 2, one can calculate, and for p greater than 2, one has to construct a local inverse. And then by a spectral sequence argument, one basically deduces everything. Sorry? This is what I explained. So if you have a lambda 0 module M, let's say, then one can construct a new lambda 0 module. I will call it M to the P, where T acts by T to the power 1 P. Okay. In any case, these algebraic considerations have a very specific output. Here, this corollary. So let's consider the total bar length. So it is the sum of the lengths of all the finite bars. Then the total bar length with coefficients Fp of the pth iteration is at least the same as is at least p times the initial one. So it grows linearly with p, except that for pth iteration one needs to choose coefficients in Fp. Okay, so it's okay. All right, and perhaps the final ingredient is that if the quantum cohomology is semi-simple, then all the bars are of uniformly bounded length. So the maximal length of a finite bar is bounded by a constant that is independent of phi. Okay. So that's where the semi-simplicity comes in. So this uses ideas of Entov and Polterovich, and also uses my previous work with Asaf Kislev. And perhaps I won't say much more about this at the moment, but you're welcome to ask me a question afterwards. For now, I'd like to give a sketch of the proof of the theorem. So let's say that K is Fp. For characteristic 0, it is a slightly longer argument, exactly because of your point of how the choice of coefficients affects things. Okay. But once we look at Fp, we can just fix Fp. Then the condition that there are more fixed points than the dimension of homology implies that there is at least one non-trivial finite bar. So beta total is strictly positive. Right? So now we can look at the total bar length of phi to the p to the k with Fp coefficients. So p is fixed. Yeah. Then this grows strictly linearly in p to the k. Okay. Or faster, of course, but okay. It grows linearly in p to the k. On the other hand, by the uniform bound from point 3, this beta total is less than a constant times the number of finite bars, but this is again less than a constant times the count of fixed points of phi to the p to the k. But if there are finitely many periodic points in general, it is not hard to conclude that this count is bounded. So that would give a contradiction. Okay, so one gets, on one hand, something that grows linearly in p to the k. On the other hand, this is smaller than something that's bounded in p to the k. So that's a contradiction that proves the result. In characteristic 0, one does not fix the prime, and then one needs to have this constant, this upper bound uniform in the prime. Okay, that is a bit of further work. All right. So that's the sketch of the proof. And perhaps I would like to end the talk today with a discussion of some further developments. So the methods of the proof of the theorem have given further results. In fact, two sets of results. So the first set of results is the following. So a result of Sugimoto from 2021 shows that if there is a periodic orbit whose loop is of infinite order in H1, and it is homologically visible, so its local Floer homology is non-zero, then there are infinitely many periodic points. And this works in great generality. Second of all, this result was extended to weighted projective spaces by Simon Allais, who used generating functions of Hamiltonian diffeomorphisms instead of Floer theory. Further, it was so the same theorem as what I have presented works in the semi-positive case for semi-positive symplectic manifolds M omega. This is a result of Marcelo Atala and Han Luo from 23. And finally, the result was extended. So Hofer-Zehnder conjecture was proven by Bai and Xu for all closed toric symplectic manifolds. So here, there is no semi-simplicity assumption. Instead, there is a proof of semi-simplicity for a suitable bulk deformation. And the second set of further applications is the following. So one can use similar methods to obtain restrictions on Hamiltonian pseudorotations. So maps which are similar to this rotation of the sphere that I have explained. Okay. So the restriction is that if you have such a pseudorotation, then there's plenty of holomorphic curves. So there's a non-trivial pseudo-holomorphic sphere through every point, for instance. But there is also an algebraic count that explains what it is. Okay, so this is the result of mine and of Cinelli, Ginsburg, and Gurel from around 2020. One can also obtain restrictions on Hamiltonian torsions, so finite order Hamiltonian diffeomorphisms. So again, existence of such diffeomorphisms implies that there is plenty of holomorphic curves. So this we proved with my student Marcelo Atala, and we have some further work with Nicholas Wilkins in hopefully 2024. And finally, something I'm currently very excited about, similar methods allow one to prove the new cases of Hilbert-Smith conjecture. More specifically, it allows one to prove the Hilbert-Smith conjecture for actions by homeomorphisms of symplectic nature. So for instance, one can rule out continuous actions of the group of p-adic integers by Hamiltonian homeomorphisms. So those homeomorphisms that can be uniformly approximated arbitrarily well by Hamiltonian diffeomorphisms. All right. And in some cases, one can generalize it a little bit to symplectic homeomorphisms. Those that can be approximated arbitrarily well by symplectomorphisms that are not necessarily Hamiltonian. So this works, for instance, for the standard torus. All right, so that is all, and thank you very much for your attention.
Thank you. Any question?
Can you explain how the condition concerning the quantum cohomology is used?
Yes, of course. Yes. So it is used here. It is used here in point 3. So we want to prove that the maximal length of finite bar, by the way, also it is called boundary depth, and it was introduced in different terms by Usher before barcodes have entered symplectic topology. So we want to bound this beta of phi uniformly in phi. So what's the idea? So let's assume not only that it's semi-simple, let's just assume it's a field. So for CPN with suitable coefficients, it's a field. Okay, so let's assume it's a field. Then one can look at the spectral norm. So it is, so gamma H is C1H plus C1H inverse. So C1H means you look at the Floer theory and you do homological minimax for the symplectic action function of H with respect to the fundamental class. Okay. And H inverse is the Hamiltonian which generates the inverse isotopy. Okay. So this is the spectral norm. It was first introduced by Claude Viterbo and then developed further by Matthias Schwarz and Young and Moore. Okay, so in this case, if even quantum cohomology is a field, then gamma of H is uniformly bounded. So this is a result of Entov and Polterovich, and what they do is they apply a Poincare duality formula to this piece and then invert something. And use the triangle inequality, and that gives you a uniform bound here. So this is number one. Number two, with Asaf Kislev, we proved that the spectral norm is always an upper bound for the boundary depth for this beta. Okay, and here one uses multiplication by continuation elements. So multiplication pair of pants, usual pair of pants product, but with Floer cycles that represent the fundamental class with respect in H and in H bar, right? And also they optimize the action. So their actions are given by this guy and this guy. Okay, and this allows you to prove that gamma is bigger than beta. And so in general, if even quantum cohomology is not a field, but it is semi-simple, so it splits into a direct sum of fields, one can split everything, including the Floer complexes, etc., with respect to these idempotents, the units of the field summands. And then one can work one idempotent at a time exactly in the same way. That proves the uniform bound here, which is used crucially in the inequality here. Thank you for your question.
Any other question?
So for the last example, I
Yes.
haven't got it. So do you mean that the Hamiltonian homeomorphism acting on the periodic numbers?
No. So I mean the following. So first of all, periodic numbers is a topological group, right? Given just by the periodic norm. And I claim that there are no continuous monomorphisms from ZP to the group of Hamiltonian homeomorphisms with, let's say, the C0 distance. One can put actually slightly different space and different distance, but for instance, this for M omega simplexically aspherical. So, right, so kind of class of omega on pi 2 is 0. Maybe just for simplicity, let's also assume that C1 and pi 2 is 0. In fact, this also works if one drops this condition or if one drops this condition. And it is expected to work for the same class of manifolds for which Conley conjecture holds. So this will appear sometime later. Yes, so how to get barcode from studying Floer theory. So I have avoided this question by telling you how to get the lengths of the bars from Floer theory. But in general, so first of all, maybe first question is how to get a barcode from studying functions and manifolds. Right, so what one does, so let's say we have this function on S1, let's say. So one looks at sublevel sets. Right, so these are certain subspaces of a manifold, and one can take homology with coefficients in a field. Here, actually, field is pretty important. Okay. Okay. So this is a vector space. This is a K vector space. Let's call it maybe VT, and then you have maps like this. And so if R, let's say, is less than S, there's a map from VR to VS given by inclusion. Yes, and they satisfy the following kind of functorial condition, right? So going from R to S and then from S to T is the same as going from R to T. Okay. So, and also it is not hard to see that, let's say, so for this particular function, this is Morse function, right? So all of these vector spaces are finite dimensional. In this case, one can prove that as a functor, from R with its order category, right, two category vector spaces, this notion is isomorphic to direct sum of very standard such things, right, that are given by these intervals. So there's going to be this one, there's going to be this one, so it goes to infinity, and there's also going to be one from here to here. Okay, so it's isomorphic to direct sum of interval persistence models. Okay, and these interval persistence models, of course, they depend only on the intervals, on the multi-set of intervals. So we just remember these intervals. Okay, so this is what happens with functions. What happens in Floer theory is something similar, except that instead of our circle, you have the loop space. Instead of the function, you have action functional, and you have to be careful. Right? So instead of just homology of sublevel set, one has Floer theory. Right? So kind of more direct analog of this picture would be to say, okay, let's look at the Morse complex of F. Let's filter it by values of F. Right? And well, we will get this picture from the homology of these subcomplexes.
Okay, so due to lack of time, we should thank the speaker again now.